If an alien civilization visited our solar system, they'd measure our progress using the Kardashev scale. It ranks a species' advancement based solely on energy, specifically how much of their host star's power they capture and utilize. To understand the gap between us and a Type 2 civilization, you have to look at the scale of the Sun. It contains 99.86% of all the mass in our solar system. From a mathematical perspective, Earth and everything on it is almost insignificant compared to that singular energy source. Right now, humanity captures nearly 0% of that total output. We are currently positioned at the very bottom of the scale, utilizing only a tiny fraction of the energy reaching our own planet. We face a physical limit on the ground. 70% of Earth is water, and much of the remaining land consists of mountains or polar regions like Antarctica. These areas are too remote or too harsh to support the massive solar arrays needed to move the needle on our energy consumption. To climb the scale, we have to move our collection arrays into space, where solar energy is constant and unobstructed. While this was once a theoretical goal, the massive power requirements of artificial intelligence are now providing a direct economic incentive to make that move. Reaching the next stage of our development means looking beyond the constraints of our geography. The solution is to begin shifting our most energy-intensive digital infrastructure directly into the vacuum of orbit. A data center is a physical facility filled with computer chips that require two things: immense amounts of electricity and constant cooling to prevent the hardware from melting. Space offers a specific engineering advantage for these systems. In a vacuum, heat can be radiated away into the void. And this eliminates the need for the complex water and air cooling infrastructure that tethers terrestrial data centers to the ground. This is the reference design for a SpaceX AI satellite. It is built to support a 150 kilowatt peak power load, roughly the same as a high-end Nvidia GPU rack. The design centers on a core compute node powered by massive folding solar arrays. The proportions are extreme. To capture enough sunlight and radiate enough heat, the satellite requires a 70-meter wingspan. The actual computer rack is a tiny fraction of the overall structure, dominated by these massive solar panels and radiators. These orbital racks will be linked together by lasers, allowing them to transfer data between satellites instantly. This network then beams information down to the existing Starlink constellation, reaching users on the ground with very low latency. Essentially, this satellite is a self-contained, solar-powered server rack. It functions as a node in an orbital network that operates independently of Earth's thermal and geographic limits. The primary barrier to this vision is gravity. Lifting millions of tons of hardware into orbit is impossible using traditional rockets that are discarded after every mission. The cost of replacing the vehicle every time makes the scale of this project prohibitive. Starship is designed to solve this through rapid reusability. By landing and flying the same vehicle repeatedly, much like a commercial aircraft, the cost of reaching orbit drops significantly. The goal is to shift from our current global capacity of a few thousand tons per year to millions of tons. This level of lift is what makes a large-scale orbital compute network physically viable. Even with the rockets in place, we face a manufacturing bottleneck. Current global chip production cannot keep pace with the demand for a terawatt-scale orbital network. To meet this, SpaceX has proposed a terafab. This facility would cover 100 million square feet, 10 times the size of Giga Texas, dedicated entirely to the mass production of AI hardware for space. By combining Starship's lifting capacity with the terafab's output, space infrastructure moves from specialized one-off launches to a standardized industrial assembly line. As we scale toward thousands of gigawatts, we eventually hit a mathematical limit. Lifting every pound of raw material out of Earth's heavy atmosphere and thick clouds is inefficient, even with reusable rockets. The Moon offers a more efficient path. It has no atmosphere and only 1/6 of Earth's gravity, making it a much easier place to launch heavy hardware into deep space. The next step is manufacturing. Instead of shipping every solar panel and radiator from Earth, we can produce the bulk of that mass locally using lunar resources. To launch these satellites without chemical fuel, we can use a mass driver. This is a linear electric motor, essentially an electromagnetic railgun, built on the lunar surface to accelerate payloads to orbital velocity and shoot them directly into space. The roadmap is already in motion. The target is to reach 1 gigawatt of orbital compute by next year, with the goal of scaling to 100 gigawatts within the next 4 years. Ascending the Kardashev scale is a matter of solving these specific engineering challenges. Through reusable rockets and lunar manufacturing, the transition toward utilizing the full energy of our solar system is becoming an active technical reality.